2.1. Find square roots and compare real numbers. Square root. Algebraically, we could define b squared equals to a. And when we square both sides, you need to set b squared equal to positive negative square root of a. Therefore, this means b is positive negative square root of a. Numerically, if I set b squared equals to 9 and take the square root of both sides, I get b equals to positive negative 3. Therefore, positive 3 squared gives me 9. Negative 3 enclosed with parentheses squared also gives me 9. So there are two roots. Positive 3 and negative 3 are square roots of 9. So what can we say here? All positive real numbers have two square roots, a positive square root and a negative square root. 0, however, has only one square root. 0. Radicand is the number or expression inside a radical symbol. Perfect square is a number that is the square of an integer. So for example, a number such as 81, positive 81, it is the square of positive 9 and negative 9. Irrational number is the square root of a whole number that is not a perfect square. It cannot be written as a quotient of two integers, and the decimal form does not terminate or does it repeat. For example, the square root of 945. I can split this into two factors, 9 times 105. I could take out the 3, but the square root of 105 is irrational. I cannot think of a perfect square in which I can make it even. So this would be equal to about 30.74085 ... And none of these numbers after the decimal will repeat, nor will it terminate. So that's why it's irrational. Real numbers. Real numbers are the set of all rational and irrational numbers. So in the rational numbers, as you can see, you have whole numbers starting with 0, followed by integers. So you got 0, whole numbers, and all its opposites. Negative 1. Okay, and in general, rational numbers can be expressed as a quotient of two integers, such as 3 over 4, or a repeating decimal. And for irrational numbers, you could have square roots that with decimals that don't terminate, nor do they repeat, or pi is a really good example. Now let's do some practice. Part A, find square roots. Evaluate the expression. So if you're given a positive negative sign before the square root, just recopy it. And take the square root of 36, it's a perfect square, 6. If there's no positive negative sign before the square root, don't worry about it. Just take the square root of 49. And this one would be negative 4, negative 25, 24, 21. Part B, approximating the square root using perfect squares. To approximate a square root using perfect squares, you have to approximate the square root to the nearest integer. First, you find the two nearest perfect squares. So, for example, square root of 51, you would have 49 and 64. And after you take the square root of 49, you get 7. And after you take the square root of 64, you get 8. And 49 happens to be closer to 51 than 64. So therefore, square root of 51 is closer to 7 than to 8. So we can say that the square root of 51 is approximately 7. Okay, and then let's do some practice. Just for the square root of 32, you have square root of 16 before that, and a square root of 36. 36 is much closer to square root of 32. So we can say the square root of 32 is approximately 6. Now for this one, the square root of 100 is very close to 103. And the next one will be 121. That's too far away. So the square root of 103 is very close to 10. And for the next one, we can say negative 49 and negative square root of 36. And 49 is much closer to 48. So negative 7. So as you can see, negative 48 is very close to negative 7. And for the next one, we could think of $361. You can also think of 324. So the square root of 361 is 19. So here we have negative 19. The square root of 324 is 18. And as you can see, 324 is further away from 350 than 361. So we can approximate negative 3 square root of 350 to about negative 19. Part C, classify numbers. Let's take a look at the square root of 24. Is that a real number? Yes. According to this chart, the square root of 24 falls under the category irrational numbers. Rational plus irrational makes real numbers. And is the square root of 24 a rational number? I would say no. Irrational, yes. Integer, no, because this will become a decimal number. And is it a whole number? No. Square root of 100 is 10. Is that a real number? Yes. Rational? Yes. Irrational? No, because it's obviously an integer. And yes, integer, whole number? Yes. Negative square root of 81 is negative 9. Is that a real number? Yes. Rational? Yes. Irrational? No. Integer? Yes. Whole number? No. 7. And for 7 and 25/100ths, that's a real number. Is that a rational number? I would say yes, because you can rewrite that as 7 and 1/4 and change that mixed number to a quotient with two integers, one in the numerator and one in the denominator. And irrational number is nope. Integer, nope. Whole number, no. Negative 15/2, is that a real number? I want to say yes. Rational, yes. Irrational, no. Integer, no, because this is actually negative 15/2 is actually negative 7.5. It's a decimal number. It's not an integer. If it's not an integer, it's not a whole number. Okay. Part D. Rewrite a conditional statement in if-then form. Then tell whether the statement is true or false. If it is false, give a counterexample, meaning an example that will prove that you are right, or why the statement is wrong. Given, no fractions are irrational numbers. If-then form. To change the given statement to an if-then form, you will write, if a number is a fraction, then it is not an irrational number. This is true, so you don't need a counterexample. Given, all real numbers are rational numbers. So if a number is a real number, then it is a rational number. This is false. A real number can also be irrational. So a counterexample would be the square root of 2 is a real number, but not rational. Word problem. The area of a square painting is 3,600 square inches. Find the side length of the painting. X would be square root of 3600. Has to be positive because the side length cannot be negative. Okay, so X is side length. So this would be 60 inches. Okay, and that concludes this lesson.